right. Hello.
Hi, Professor.
How are you?
I'm good. How are you?
I'm pretty good. What you got in mind for us right now?
I just want to know if we can do like one or two practice mechanisms from one of the past tests.
Oh, absolutely. Got any particular ones in mind? Sorry, I got a little mess left over from dinner here. Okay. All right. I've got exams ready right here. Just getting the right course. And go ahead. Semester and test.
From fall 20.
Test 2, fall 20, test 3. Test 3?
Test 3, yeah.
Okay, fall 20 coming right
Some of the
up.
questions from the bottom. I think it's like part 6.
All right. Oh, I hit the layout button. Test 3 key. Is there the original test here at all? Or hang in there. Here we are.
I'm sorry, no, part 4.
Part 4. Okay, I've got it. Let me share my screen, show you what I got. Zoom screen. All right, moving through part to 4, and we've got nice one here. We're supposed to do the mechanism with labels. You want to? That's a nice introductory one.
Yeah.
Okay, let's start with that one. And Snippy Doodle is here. And here we go. Fall 2020 coming right up. Minimize. Paste. Okay. Z. Paste. There we go. So we're going to do this. And I need to find my pen. Stuff's moving around today. There it is. Okay. So I'll probably edit the start of this segment down. We're going to do fall 2020 test 3, part 4, question 1. We need a mechanism that accounts for all products below. And this is a reaction with HBr, a hydrohalous acid, and an alkene. That's our first mechanism we ever learned in chapter 6. The alkene pi electrons are attracted to the very positive hydrogen, and you generate 2 carbocations. How do you know you're going to need to show both carbocations? Well, I've got a mechanism that has a product that comes from that one. It's the second one. And sorry, I've got another product that comes from this cation, which I will form in much smaller amounts. That would be the first product where the bromide ending up on the end. And this one ends up with a bromine on a carbon where there was no cation to start with. That one must involve rearrangement. And what has to rearrange? Well, this one is not a candidate for rearrangement because the adjacent carbon to the carbocation is not branched. That is what you look for first. This carbon with the cation here and the adjacent carbon branched is a candidate for rearrangement. So I'm going to show you what happens to a second version of that cation. The first version is going to generate product number 2. And this version here is going to have this H, which is not in the product. There's no H on this carbon here, so that H that's here must move. It's called a hydrogen shift, and it shifts to the adjacent carbon. Why does it do that? Because it generates a more stable tertiary carbocation, and you're going to have to include that as part of your answer. There's that lovely tertiary carbocation. When we generated the first cation, sorry, we generated a bromide. Every time you generated a cation on a carbon, you generated a bromide ion as well. When you generated the other carbocation, you made a bromide. You're going to need them all. And the rearranged one brought its bromide with it. We'll put it up here. We need those because that's how we show how this bond is made. If we use the pair of electrons and go all the way up to the carbon, that will generate the second product. Second product. We need our reaction arrows to have a different color. Get some green going here. And this one here, attacking the carbon there. I don't want a lazy arrow. No lazy arrows. It goes to the carbon and it generates the first product. That product. And this last one, attacking the carbocation that's tertiary, generates this product here. And we're going to circle that product. And we're going to talk about why it's the major product. Circle the product, explain your choice. Your circle has nothing to do with the stability of this product compared to this product compared to this product. No, it has to do with the stability of the rate determining step molecules, which are the carbocations. The slow step is generating carbocations. You need to talk to me about the stability of this carbocation. So in part B, circle the major, explain your choice. We've got the circle. There's your 1 point. I think you get 3 more points for saying right down here. This tertiary C+, you don't even have to write the word carbocation. You can write C+, has the most hyperconjugation. I need the magic word as part of your answer. And because it's the most stable, because of hyperconjugation, it forms faster. So there we go. And that is all the points except for part C. Part C is going to be on your first question of your short answer, and it's worth a lot of points for not a heck of a lot of work. We're allowed to use the short forms, Lewis acid, La. Remember, that's also electron acceptor. Definition of a Lewis acid's in those 2 initials, if you don't spell electron with an E. And the acceptor is here. We'll put our labels in pink. Lewis acid is always an electrophile. Yeah. Accepts them because it loves them. And you'll also get a Bronsted label if the thing accepting the electrons is a proton, which it is. So it's also a Ba. I like to say Ilaba. It sounds like a name, but those things work for me, not for everybody else. I got a very sound-oriented brain. Aural, they say, Aural. And the what reacts with Lewis acid is a Lewis base. It's donating its electrons to the positive hydrogen because it loves positive, nucleophile. And this one's donating electrons to a proton, so it's also a Bronsted base. And I like to call that a Lubnu Habibi. It just helps me remember it. Okay, so now we've got these guys all doing the same thing. Every cation's reacting with a bromide here, here, and here. Same labels each time. The cation's accepting electrons. It's an Ela. I'm going to put them in that order from now on. Ela sounds more like a name to me. You cannot put Bronsted acid on this one. The acceptor of the electrons is not a hydrogen atom, it's a carbon. And Lubnu. Lubnu for every bromide that attacks the cation or a cation. And Lubnu here too. Each of these labels is a half point. These points are starting to add up, aren't they? The attacked cation is an Ela every time. And where do I not have an Ela? Over here. Please don't label a molecule that's not reacting with another molecule. Don't label this thing. You can go ahead and put labels on it. I'm just not going to give you points. It's a hydrogen shift. And yeah, we got that question done.
Okay.
Yes,
So,
sir.
Professor, okay. So for this specific mechanism, like with how it's reacting with the double bond, so the electrons from the double bond go
From
to
the pi bond. Yes, only the pi electrons. Yes.
Yeah. That goes to the hydrogen, and then what's
Yep.
connecting the hydrogen and the bromine,
Mhm.
that would go back. That would go to the bromine.
Yeah, that sigma
right?
bond's becoming a lone pair on Br. I showed it here
Br.
because I need to use it here. Yeah, so it's
Mhm.
bromide now. Yeah.
And then you want us to like, not like you want, but like, and we're supposed to like show that it's separated with the electrons, and then show how the electrons would bond.
Yes. I need to have. Here's where your points are coming from. This arrow must, and there's no exceptions to this, this arrow must clearly start on the pi electrons. If it starts anywhere else, there will be a deduction. This arrow must end at the hydrogen atom. If it ends anywhere else, there will be a deduction. This arrow must start on the middle of this bond. Arrows always start at a pair of electrons. That's what these arrows are, moving electrons. And it starts at the pair of electrons in this bond and ends on the bromine atom. And there are those electrons right there.
Yep.
And here, and here.
Okay.
You know, bromide really has 4 lone pairs. I don't need to see all of them. I only need to see them if they're relevant.
Okay. So since only one of them is going to be bonding, like
Yes.
one of the electron pairs, that's why we only have one electron.
That's what, yeah, we know there's 4 lone pairs there because we did Chem 141.
Yeah.
You don't have a minus charge on a bromine unless it's got 4 lone pairs.
Okay. So, and then for part B, so let's say, for instance, like, I don't know if this would happen, but like if there was like 2 products, right? And one was a 1' carbon and the other was 2'. So the 2' would be the major.
Yep.
Because it'd be more hyperconjugate, right?
Yes, the cation that made it, you'd have to make your explanation on the cation that made it. So pretend this guy's not around and you're comparing these two. Well, if you had to choose between these two, you'd be picking this one, right?
Yeah.
And you'd have to use the same words, but you'd say this secondary cause C+ has the most hyperconjugation, so it forms faster.
Okay. Okay, I just wanted to clarify.
Good one.
Yeah.
Right. So we'll come back with another segment. Do you have something in mind from the same test so I can have it ready before we get back?
Yeah, maybe just like the next one.
The next mechanism question? Okay, we'll do that. So I'll see you very soon. Trying.